Not just 25, but at least 25. Does somebody notice a shortcut? I can do 1 minus the thing I left out. So that's an extension of that at least 1. If the reverse probability, if the complement is quicker to do that. Right? I can add all those up. That's not really that hard. But I know it's got to equal 1 minus this, because altogether they have to make 1. So on this one, at least 25, it'll be 1 minus 0.05, 0.95. Now, if you add all these up, some of you guys might have done it, you should get 0.95. Yeah?
Wait, for number A, how did you get that again?
There's 2 things I have to check. To make sure it's valid, all the probabilities have to be 1. If they're less, that means I left something out. If they're more, that's freaky. Right? And they all have to be between 0 and 1, of course.
So is that just the case for everything?
Yeah, all probabilities have to be between 0 and 1. And for distribution, they have to add to be 1. Or else I left something out. Right? And when I try to make my own, like this one, as I'm doing it, I'm always thinking, how much do I have so far? How much do I have so far? Because I have to make it come out to be 1 for it to be valid.
So it wouldn't be valid if it wasn't.
Exactly. Wouldn't be valid. The math that we'd want to do, if it didn't add up to 1, the math would actually not come out right. Yeah.
I don't get it. I don't get why it's 1 minus 0.05.
Oh, what, real quick, we do it up here, it might be easier. All right, real quick. What's the probability of 21 plus the probability of 25 plus the probability of, what was it, 30, 40, 50? What's all that?
100%.
It's got to be 1, or 100%. So 1 is a decimal, is that cool? And it is, we checked it.
Yeah.
So, what's the probability? 25 or more? Isn't that all those? Wouldn't that be 1 minus the one that I left out?
Yeah.
All right.
Okay.
So on one level, I like doing this. Some people don't like it because it takes them back to the algebra days, and that might be traumatic for some of us. But it's not that big of a deal here. But also, it just kind of makes sense. I know they have to add up to 1. So if I leave 1 out, the rest must be 1 minus that 1 I left out. That's all that is. And it's more generalization than just probability of at least 1 is 1 minus none. This is in general. The probability of something is 1 minus whatever I left out. Yeah?
So for the last one, it's like how many kids in the survey believe they returned before 50? So would that be kind of similar? You would just leave 50 out, or like?
Oh, we'll get to that. Don't worry. Yeah. And we could do that now.
Is it kind of similar?
This is a question of how many, though. And I've got 200 kids total. So before age 50, what's probability that, what's the percentage of kids that think they'll do it before 50?
74.
Yeah, 0.74, 1 minus 0.26. And so then to figure out how many kids from my survey believe that, I would take 74% of 200. Cool. 0.74 times 200 will tell me how many kids thought that way. I love it. So 148 kids must have felt that way because that's where the percentage would have come from. Right?
How did you get the 74?
Well, how many people believe they'll retire at age 50?
Before.
26%. Right? 26% right there. So how many believe it's going to be before that? 1 minus that. Yeah. The rest. So what about part C? I'm going to have to go back and forth between my calculator. But we already know part C here, don't we? The mean is 35.3. Filling in this formula. What number goes here? Yeah, 1347.3. Minus, and we just figured out what the mean is. And whatever that is. 101.21. 101.21. Oh, 101.21, yeah. And then how do I get the standard deviation? Square root. And what's that? 10.06. I like it. Cool. You guys doing okay so far? So this should feel very familiar. It's actually a much easier table than from chapter 3 if you think about it. I'm hoping that most of us are used to, if you cover the summation, it tells you what kind of column you need before you can add them up. Okay? And of course we know to get the standard deviation I have to square root the variance. Cool. Now one thing that sounds very familiar that you have to be careful about, I'm going to ask you this kind of question a lot. Right? Because it's the foundation of a lot of our biggest theorems in statistics is the percentage that are in certain places. So I like to do not theorems, I like to do concrete data. You can actually go see what percentage is in there. So the mean was 35.3. If I add one standard deviation up, if I go up 10.06, I end up, I love it. And if I go one standard deviation down, I go down 10.06, I end up, I love it. You guys with me? I mean, we've done that kind of thing before, a lot. Which data points actually fall in there?
30 and 40.
Yeah, 25 doesn't, 30 does, 40 does, and 50 doesn't, right? Now you got to be careful. You can't just say then 2 out of 5, 30 and 40 are in there, so 2 out of 5. What percentage is actually in there? There's the percentages, right? So 30 and 40 are in there. So it'd be 0.32 plus 0.16. 48% is in there. So does it sound like this would be a normal distribution?
Not exactly.
No, because it should be what?
68.
68, or at least close to be a candidate, right? I like it. Yes, sir.
Is normal, like, if you're thinking normal distribution, does it absolutely have to be 68, or can it just be, like, close enough?
That's what close enough is fine. For it to be approximately normal, yeah.
Would that be close enough or no?
Hell no, yeah. I mean, we're going to firm up some of these things later, and that's why right now we still have to have it pretty damn far away to be able to say for sure no. But if it was like 63, then it's getting gray. It's like, is that close enough now?
Yeah.
We don't know yet. All right, how are we doing? These are questions that sound very familiar, and they're the same questions. And one thing I want to make a big point of right now that I didn't earlier is every time you have a different way to present data. I could do this. I could use the old formulas from chapter 3 to figure out the mean and the standard deviation. That would so suck. Because in order to do that, I need to make this into a list of data. Well, how many 21s would I have out of 100? 5. And how many 25s? 21 of them. Do you really want to work with 100 data points? Not really. So there must be an easier way to get the mean and the standard deviation. And there is, this way. So every time they give me data in a different way, I want to figure out a new way to find the mean and the standard deviation. A quicker way. How we do it? Yes?
For all these, we're supposed to assume population, not sample.
Yes,
right?
exactly. I'm glad you said this is considered a population.
Yeah, this sample.
And it pretty much has to be considered a population, to tell you honestly, because P will always have on the bottom N. You can adjust it to be considered a sample, but it's going to have N on the bottom. Yeah. And of course, a sample should have N minus 1.
Yeah.
Good.
So like as a test question, you might give us like the table without without like the equations, and then we have to fill it in. And
Oh hell yeah! Sorry. Yeah, no, don't expect those on a quiz or a test. Yeah, this is just for a handout, just so you can get used to how to put it in.
Okay.
Yeah, and to tell you honestly, if you really wanted to, you could do L1 squared times L2 to get this one, couldn't you? You could do L1 squared times L. I don't care. Whatever gets you X squared times P of X.
So I'll have to know that the XP of X. And
Yes, so these are two formulas that you can now add to formula sheet. Yeah, so on the day of review, those are two that I'll say you can put on your formula sheet. Cool. All right, so I desperately want to preview the next couple sections and then to let you, I don't know if I'm going to do this to you yet or not, we'll see. So let's see. here's, we just learned a new way to represent data. And it's actually not a new way, because we did this with histograms. We made relative frequency distribution, which is really all a probability distribution is. How are we doing this so far? And what I just said was, anytime they present data to me in a different format, I want to figure out new formulas for the mean and the standard deviation. So here already is our next format. What's easier, like the key part of this word binomial? Phi. So that means there must be somehow two parts involved, right? So for a binomial distribution, there's always exactly two possible outcomes. Okay, and those outcomes have probabilities P and Q. So P is, let me do this. I don't have the most time, so I want to use this effectively. I'm going to kind of get us into where the formula comes from, and then I'll finish discussing the generalizations of binomial distributions. But the main thing is that there are two possibilities, and that they have probabilities that I can assign to them. So for example, I know I use this, overly use this, but oh well. It just makes it easy for this. Let's say 11% of the U.S. is left-handed. I keep using that stat because that's the last. Did you say that was Q? P and Q, yes. It's trying to be a Q. Now, if I pick 5 people, this is going to sound very familiar. It's going to feel like you're back in chapter 4, but you're not. You're not going to be left dangling as much as you might have felt before. It's going to be a specific way to do these. If I pick 5 people, I want to know the probability that exactly one of them is left-handed. You guys get this? Understand the question? How do I set this up? Well, let's first define a few symbols. Probability of L for left-handed, what would that be? 0.11, right? And what's probability of not L? I won't say R, because there might be some people ambidextrous. They don't call themselves right-handers. 0.89. Okay, so to get us started. And let me say this is going to be P, and this is going to be Q. That's what I mean by P and Q here. Just give them some symbols to make it easier to identify them in general. You guys kind of still with nothing major there. P is considered success, and Q is failure. Success does not have to be a happy thing. It could be a dead body. If I'm looking for dead bodies, P will be the probability of finding a dead body. It's whatever I'm looking for. What am I looking for here? Left-handers. So what's probably success? Probably left-handed. So tell me one way I could pick 5 people and one of them is left-handed. And I was kind of doing this earlier. Because exactly one of them is left-handed. It could be the first one I picked, right? And then the rest of them are righties or ambidextrous or whatever, at least not left-handed. Or, and of course you start, maybe hopefully you see now you just kind of float the P through. You understand? Sounds a little bit sideways, but oh. Q, P, Q, Q, Q. Or Q, Q, P, Q, Q. Or Q, 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 P, Q. Or Q, 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 Q. And that gets old, right? Pretty quickly. It's only 5 situations, but that got old pretty quick. So thank God, if I had 80 people, this would so suck. But there's a much better way to do this. All of these look like what algebraically? We've done this before too. They have 1p times 4 q's. You with me? No? Yes? I heard a no. It's okay to be honest. I like honesty. You don't have to make me feel good. But I'm hoping, we've seen this kind of thing before, so I'm hoping that's making sense so far? Now, the issue is, to get the whole probability of getting one left-hander, it could be this, or this, or this. And the reason we multiply here is because it's and, right? First one's lefty and, the second one's not lefty and. But what do these ors mean? Addition. So how many of these do I have? And they're all the same, so won't I have 5 of these then? That's a nice little compact formula there, isn't it? There are 5 to get the probability of one left-hander. It'd be 5 ways to do it times PQ to the 4th, because I want 1 success, 4 failures. You with me so far? So now I just got to throw the numbers in. P is 0.11. Q is 0.89. So the one last, and you can type that in your calculator, is everybody cool with that? The one last piece is, can you imagine if there were 80 people, and let's say I want exactly 4 of them to be left-handed. Can you imagine how long this list would be? Do I want to find out this number by making the list every damn time? Are you guys with me? This sounds like I was saying before, oh God, there's so many freaking ways to do it. Yes. So thank God. The one thing I got to show you to finish this out for us is the calculator can count how long the list would be. There's a series of buttons I could press, and it'll tell me this is how long the list would be. 1,400,000. You're like, thanks, calculator. I really didn't want to write that down 1,400,000 times. So that's the one piece I have to show you next time, is how to get that number. Thanks. The magic phrase. Come on, you go. Oh, yeah. Yeah, the 4 home runs. Yeah, so like 3, 3, 4, if you're not done with it, I'll come into the next one.
I was thinking, like, I don't know if it's higher.
Oh yeah, turn it in. Earlier is better, because then I'll have time to actually look at it.
This should have 5 options. Yes.
No. But good. Anyway, you're the one that needed to finally run. Whatever you got in chapter 4 then. So really, just on Monday, chapter 4 homework, that's the next thing we really think about there. Yep. Really? Oh yeah. Correct. And the corrections, like always. Oh. Oh, there's your to the button. To the 10th button. And the thing is, just in case this comes up later, you have to do 0.249 to the 10th, and then you have to multiply by something else. You have to push over to get down, and then you can do times 5 or whatever. Cool. Okay. That means times 10 to the, yeah. So you put move it decimal back. So it's like if there's -7, there'll be 6 zeros. There's always 1 less 0. Here's your to button. So you do 1 minus 952, 952, to the 4th.
Oh.
Yeah. Minus 0.952, yeah, that's good. You got 186 in there. This is from the other day, right? Yeah. I think that's, this is, number, yeah, it's 0.048. 0.048. That shouldn't change. 186 and I put 186
Oh, okay.
in class.
Okay, my question was how can I find the number because that's for.
Oh, just by itself? There's,
So just
and then you can do, 0.95 to the fourth.
Oh, okay.
And you go 1 minus second A and S for, so do 1 minus that. Like that.
Oh, yeah. Okay, thank you.
Sure.
Just had a question. The bottom of the
Oh yeah, so you know there's 200 kids. And you know that 74% think they'll retire for 450. Again, our polos. So 74% of them think they'll retire for 450. So 74% of 200. So then you just multiply those. 0.74 times 200.
So I don't get why it's 74 because there's 2 points.
Oh no, so part E is different from part D. So part D is, you'll take 30 and 40, they're within 1 step away. 30 and 40, so then you add up, then you get 0.48 there, if you add up their percentages. So that's why there's 40% in there. This is a completely different question. How many believe they'll retire? Well, 74% of them before 50, right? 50 is 26, so below 50 adds up to 74. 74% of 200. Cool.
Oh, and how do you get into? I haven't used the math lab yet. How do you get into that?
Enrolling in Math 160 actually